In this video, I'm going to solve these questions. So here the question is in equal to 0 to pi by 2 cos nx dx, where n is a positive integer greater than 1. Then we have to show this, okay? And also we have to find this. So the first part to show this we have done already in the previous videos. I have explained you how to do this. So here to solve this, I'll take x equal to sine theta. Then if I differentiate this with respect to theta, then we get dx by d theta equal to cos theta. So this implies dx equal to cos theta. So when x is 0, so which value of sine give you 0? Sine 0 is 0, so theta will be 0. When x is 1, which value of sine give you 1? That is nothing but pi by 2, so theta is pi by 2. So I'm going to substitute the value here. So we get 0 to 1. Here I'll substitute in place of x as sine squared sine theta. So we get sine squared theta square root of 1 minus sine squared theta dx is cos theta d theta. So we have sine squared theta, 1 minus sine squared theta is cos squared theta. So we get cos theta into cos theta, which is cos squared theta. So since we have to apply that reduction formula, this sine squared theta I'll change as 1 minus cos squared theta into cos squared theta. You multiply this, so we get this. So we apply the reduction formula here. So we get here 2 minus 1 divided by 2, I 2 minus 2, minus, here n is 4, so 4 minus 1 by 4, I 4 minus 2. So 2 minus 1 we get 1, 1 by 2, so I here we get 0, so cos theta to the power 0, so this will contribute to 1. So we have to integrate d theta. So if we integrate d theta, we get theta. Then we apply the limit 0 to pi by 2. Here it is 2. So we apply, now n is 2, so we can use the formula again. So we get 2 minus 1 by 2, I 2 minus 2, that is 0. I0 means cos theta to the power 0, d theta. So this will give you 1. So we integrate d theta, we get theta 0 to pi by 2. So if I apply the limit, we get here 3 pi by 6, pi by 4 minus 3 pi by 16. If you do the LCM here and simplify this, we get the answer of this integration to be pi by 16. So we have derived the integration by using the reduction formula here. So suppose you have this question. This is your question here. 0 to pi by 2, jn, I'm donating this as my jn equal to 0 to pi by 4 tan nx dx. Show that this, so we know jn 0 to pi by 4 tan nx dx is equal to this. Now in place of n, let us replace with n plus 1. So we have here n plus 1, here also replace with n plus 1. So we get jn plus 1 equal to 1 by n minus jn minus 1. Bring this one to this side, we get plus. So jn plus 1 plus jn minus 1 is equal to 1 by n. Now we want to reduce this. So I have donated this as in equal to integration e minus x to the power n dx. Then we have to show this. So I took in equal to integration e minus x to the power n dx. So I use integration by parts. So this I'll take as my first function. This I'll take my second function. So we get x to the power n integration e to the power minus x dx minus integration differentiation of x to the power n integration e to the power minus x dx. So if I integrate e to the power minus x, I get nothing but e to the power minus x by minus 1 minus, and if I differentiate this, we get nx to the power n minus 1. If I integrate this, okay, so I get e to the power minus x by minus 1 dx. So minus minus we get plus, so we have plus here. N is constant, we come out of integration, so we get this. So this is nothing but in minus 1, so we get this. So hence we have proof. We have shown that. Now we try to do this question here. Okay, so here in is okay. So let us reduce the first part. Here in is equal to integration integration x to the power n cos ax. Okay, x to the power n cos ax dx. So this is your integrate x to the power n cos ax dx. So you apply integration by parts here. So here we have x to the power n integration, okay, so cos ax dx minus differentiation of x to the power n integration cos ax dx whole thing dx. Okay, so we have this as x to the power n. This is minus sine ax by a, sorry, it is integration cos ax is sine ax by a, so we get this minus differentiation of this, we get nx n minus 1, and integration of this is nothing but sine ax by a dx. Okay, so this is x to the power n sine ax by a minus n by a is constant, so will come out. So we have x to the power n minus 1 sine ax by ax dx. So this is nothing but j n minus 1. Okay, so you replace this one with j n minus 1. So we get here sine ax by a minus n by a j n minus 1. Okay, so this is in, so you multiply throughout with a. So we get a in equal to x to the power n sine ax minus n j n minus 1. So we get this. So this is the first proof for Roman 1. Okay, and for Roman 2, if I take this as jn equal to x to the power n sine ax dx. Okay, so I have this. I'll apply integration by parts here. So we have x to the power n sine ax dx minus d by dx of x to the power n integration sine ax dx by into dx. Okay, so this will be x to the power n, integration of this is minus cos ax by a, minus this will be differentiation of this, we get n x n minus 1, and integration of this we get minus cos ax by a dx. So this will be minus x to the power n cos ax by a minus we get plus n by a integration x to the power n minus 1 cos ax dx. So this is nothing but in minus 1. This is in minus 1. So we have here minus xn cos ax by a plus n by a in minus 1. Now here we have, this is your jn. Okay, this is your jn, this is jn. So if we clear with this, this is jn. Now you multiply throughout with a, so we get ajn equal to minus x to the power n cos ax plus n minus 1. So this is the proof of the Roman 2. Now for the proof for the Roman 3, we can follow from here. So we have this in equal to this. So use integration by parts here. So we get this. So till here I have done already. So we get, again you apply integration by parts here. So we get this. Okay, so we have got this by integration by parts. So this, if we take n, if we multiply here, we get n minus 1 by a squared. So we are left with integration x to the power n minus 2. This is minus minus. So minus plus into minus, again we get minus. So this is n minus 1 by a square in minus 2. Okay, now you multiply here with a everywhere. So I have done already here also. This I'm taking from here. So we have done by this. You multiply throughout with a square. So we get a square in equal to axn sine ax plus nx to the power n minus 1 cos ax minus n minus 1 in minus 2. Okay, So we have this. Now from here, this x to the power n can be written as x to the power n minus 1 into x sine ax plus n x to the power n minus 1 cos ax minus n minus 1 I n minus 2. From here, we can take x to the power n minus 1 common. So we are left with ax sine ax plus n cos ax minus n minus 1 I n minus 2. So that is the proof for Roman 3. Now for Roman 4 here, we'll proceed in this way. We use integration by parts, so we get this. So this we have derived already. Again here you apply integration by parts. Okay, so you apply integration by parts here. So we got this. Okay, we are getting this. So from here I have reduced already here. So we take this one, we got this. Now you multiply here. If you can see here, this, okay, this here I'm multiplying both sides with a square. Okay, so we get a square jn equal to minus a xn minus 1. Here I'm separating this x to the power n. I'm writing as x to the power n minus 1 into x cos ax plus n xn minus 1 sine ax minus n minus 1 jn minus 2. So we get here a square jn equal to x to the power n minus 1. I take common here. So this will be, I have taken common here. So I am left with n sine ax, this one, n sine ax minus a cos x, here a cos ax minus n minus 1 jn minus 2. So that proved the Roman 4. Thank you.